Hello, my name is Zawadi Mdoe, and I'm going to present about Adaptive Horizon Multistage Nonlinear Model Predictive Control. I'm a PhD candidate under the supervision of Johannes Jaschke at the Department of Chemical Engineering at NTNU. And in brief, we could say that we want a controller that is robust and most likely not to break any constraints in our processes. And we formulate our controller in a multi-stage formulation, as you could see here on the right, that once we start from the initial state, we discretize our uncertain parameters as these, and they are branching in forward in the horizon or prediction horizon. But then we will make this problem intractable if we have a very large prediction horizon. So we shorten it, the branching at NR, and what we want is a prediction horizon that is just long enough, and that is what adaptive horizon is going to do here in this case. And how we're going to determine this long enough prediction horizon is by using NLP sensitivities, and by first determining what are the terminal conditions that we know that our controller will always will at that when it meets those conditions, we know that we are at the terminal region, so we don't need to extend our horizon because it will remain stable. So this multi-stage NMPC formulation, I could see that the number of constraints increases with the size of our scenario set C, and the number of variables also increases. But our assumption is that for each realization, we have a stable equilibrium point at which the system is asymptotically attracted. And then we have an infinite LQR controller at the terminal region, which stabilizes our system. And that is the LQR control law. And then we also assign the cost of this controller to the terminal cost. And since we are linearizing the process for the infinite LQR, we assume that the terminal region is bounded, and the boundedness of the terminal region helps us to define these regions. And once you could see this in this illustration that there are three scenarios, and this is how they enter the respective terminal regions. So we're going to pick the longest terminal region, the longest horizon corresponding to the scenario. This is the algorithm. So if you have an initial n, long enough n, then you want to solve the problem, but then you're going to solve also another sensitivity, a linear sensitivity problem to determine what will be the solution in the next step. And then from that solution, you can predict what will be the horizon length long enough for that, the coming or the problem in the next iteration. This is a simulation case study, and you have A going to B and also going to D, and you have a cooling jacket. And we want to control CB to the set point. And you can see that the tracking performance is quite similar to the original ideal multi-stage controller. But then you could see that the computational times are decreased by 3-fold at least for the robust horizon of 2. And yeah, seems that in this case, the controller has the same tracking performance as the multi-stage NMPC. And also you have significant reduction in the computation time. So we have a small computational delay, which makes our control performance good. And then we have also a minimum amount of variables, just enough to solve our problem. So we are optimizing on how we efficiently use our memory. And this could be used in limited systems and beneficial in probably embedded systems.